Okay, this is part 2 of lecture 5. I will continue with the proof of the final theorem for the chapter, that there are only 5 regular solids. So from part 1 we completed and investigated this table, so all I did is rewrite once again the table from the first page and notations that I'm using: V vertices, E edges, F faces, number of sides on each face, I'm calling that little s. C is the number of sides coming out of each vertex. We also established that these two formulas for two different ways for computing the number of edges on each polyhedron, and both formulas work. The first one is F times faces times sides on each face divided by 2, and the second one is vertices times sides coming out of each vertex, also divided by 2. In part 1 we also talked about the Euler's characteristic, V minus E plus F always equals to 2, and this is a property of any convex polyhedron. This is something that Euler proved in the 1700s, although it was a relationship that was known before, thousands of years before, but it was proved by Euler much later. Otherwise is known as the Euler's formula or Euler's characteristic. So what I'm saying here is that any convex polyhedron should satisfy the Euler's characteristic. So why there are only 5 and no more? We shall proceed here by contradiction. So let's go and assume that there are more than 5 regular solids. So at least there is one more. Let's assume that. So assume that there are more than 5 regular solids. So say there is another one. Say there exists another one. For lack of a name, since I don't know exactly what this polyhedron will look like, I don't know how many faces it will have, I don't know how many corners or vertices it will have, what the faces will look like, and so on. So since we are assuming there is another one, let's call this the sixth hedron, again, because I don't know what it will look like. So at the very end we shall contradict ourselves, meaning we'll use some logical steps based on what must be true for any convex polyhedron, and show that this sixth hedron is in fact a non-existahedron. So let's see. Okay, we know the very first 5 ones. We know what tetrahedron looks like, we know what cube looks like, we know what the octahedron is, the decahedron, icosahedron is. So we are going to use the very same notation for vertices, edges, faces, number of sides, and on each face and number of sides coming out of each vertex for this other one too. So we'll use the same notation as for the others. We'll use the same notation as other 5 solids. For vertices, edges, faces, etc. Okay. So the moment that we actually decide what S is and what C is, then we'll have will have an actual image of what this polyhedron will look like. Well, what is S? S would be the number of sides on each face. Knowing what S is, it means that we will know what sort of polygon the faces of this other sixth polyhedron will look like. So if I know what the faces look like, then we're good. Again, also, if we know that what would be the number of sides coming out of each vertex, then we can completely determine the looks of this other polyhedron that, again, we don't know what it looks like. So what are they? For sure we know that S must be greater than or equal to 3. It cannot be 2, because if it's 2, it would not be an actual face on a two-dimensional space. So we know that S has to be at least 3. So 3 or higher. Maybe this polyhedron will have faces as triangles, but maybe more than these numbers, or somewhere in between this numbers, actually. I don't know, but it's very possible that the faces of this polyhedron may be triangles. So that's why we're saying it has to be 3 or higher dimension, meaning 3 or more sides on each face. That's for sure. The same thing with C. C has to be greater than or equal to 3, meaning it has to be at least 3, because if it's not 3, then it's not actually a corner in a three-dimensional space. It takes at least 3 sides coming out from a point to form a corner in three dimensions. Okay, so since this will be, we assuming that it will be a regular solid, then most certainly it has to satisfy the Euler's characteristic. So also the sixth hedron must satisfy Euler's characteristic V minus E plus F equals to 2, like all other convex polyhedra do, as all other convex, regular, and regular polyhedra. Okay, from first part, so I'm going to start with the Euler's characteristic here. This should be true. No matter what this polyhedron looks like, this definitely has to be true, meaning this polyhedron has to satisfy the Euler's characteristic. From first part, using those two formulas here, I can determine a formula for F and for V. So again, from here, F is equal to E times 2 over S, so 2E over S, and from here, V is equal to 2 times E over C. I mentioned these two formulas in the first part. So in Euler's characteristic, I'm going to substitute V and F with whatever V and F are from here, meaning I'm going to rewrite Euler's characteristic completely in terms of E. So the only variable in that equation will be E. So V is equal to 2 times E over C minus E stays as it is, plus, instead of F, I'm going to write whatever F is in terms of E, so 2E over S. Actually, E is not the only variable here, but I want to completely write this now in terms of other quantities other than V and F. Okay, so from here, I can factor out, what can I factor out? I can factor out E. Okay, So let me factor out e. So when I factor out e, I have 2 over c minus 1 plus 2 over s equals to 2. All right, so let's talk about this for a little bit. Now, I know that the number of edges definitely is a number that is positive in this context. So e is a positive quantity, 2 is a positive number. So whatever this other quantity is, it definitely has to be a positive quantity. I cannot multiply positive times negative giving me a positive number. So since e is positive and 2 is positive, it means that 2 over c minus 1 plus 2 over s is a positive quantity, since e is positive and 2 is positive. Okay, so from this inequality I have the following: 2 over c plus 2 over s, it is greater than 1. If I take this minus 1 and throw it on the other side. And I'm going to investigate this other inequality now. Okay, so what could possibly c and s be? Well, I know that there have to be at least 3. I also know that whatever they are, when I plug them in this inequality must be true. So let's work at some numbers. I know the floor, or the least value for each, should be 3. Is there a largest value that could possibly c and s be, such that when you plug them here, this inequality is true? And that is the key. So, for example, could both c and s be as large as 6? Either one or both be as large as 6? No, because if you were to plug c or s being both 6 here, you'll get a number that is less than 1, not greater than 1. Also, if one is 5 and the other is 6, you will also get something that is less than 1. So I need to write this down. All right. Note here that c and s cannot be larger than 5 or 6, because if, for example, they are both 6 or higher or larger, then the quantity 2 over c plus 2 over s will be less than 1, not greater than 1. 2 over 6 plus 2 over 6 is 4 over 6, and 4 over 6 is not greater than 1, is less than 1. In fact, the larger these denominators become, the smaller and smaller this left-hand side becomes, certainly not greater than 1. So we have a very small window to work with. We know that they can be as large, as small as 3, but no more than 5. No more than 5. So what are the possible combinations for c and s being either both 3, both 4, both 5? Let's say s3 and this 5, s2, s5 and this 3, and so on. So let's create a table and see what the possibilities are for this. Okay, so I'm looking now for, we shall consider, we'll consider all possibilities. Okay, so in this table, so this is C and this is S. What are all possible scenarios? Well, let me see if I have enough space. 3, 4, 5. Okay, I do. So this is 3, 3, 3, 4, 4, 4, 5, 5, 5, and this is 3, 4, 5, 3, 4, 5, 3, 4, 5. These are all possible combinations. Keep in mind, I know that C and S cannot possibly be 6 because it will not fit in this inequality. So all possible combinations between C and S are these numbers, both 3, C3, S4, C3, S5, C4, S3, 4, 4, 4, 5, 5, 3, 5, 4, and 5, 5. Well, okay, now we take all these combinations and we plug them here and we see what we get. Okay, so C3 and S3, C3 and S3, I already know that this combination will give me the known tetrahedron. So this combination is just tetrahedron. So C3 and S4, C3 and S4, C3 and S4, this combination gives me what I already know to be the cube. Okay, so this combo is the well-known cube. Okay, what about 3 and 5? So C is 3 and S is 5. This combination gives me the well-known dodecahedron. All right. Combination 4 and 3. So C is 4, and S is 3. That's the well-known octahedron. Okay. So what about a combination 4, 4? I don't have a 4 and 4 here, but if I was to plug 4 here and 4 here, I will have 2 over 4 plus 2 over 4, or 4 over 4, and 4 over 4 is equal to 1, not 1. So this is not a possible combination, so I will write impossible. Why? Because if I fit these numbers here, I'll get, since 2 over 4 plus 2 over 4 is equal to 4 over 4 is equal to 1, and that is not greater than 1. Okay, what about 4 and 5? Combination 4 and 5. Again, if I was to plug in 4 and 5 here, what would I get? I get 2 over 4 plus 2 over 5. That is actually equal to 9 over 10, which is also impossible. So this is an impossible combination as well. Since 2 over 4 plus 2 over 5 is equal to 9 over 10, and that is not greater than 1. Okay, what about the combination 5 and 3? C is 5 and S is 3, well, that's the icosahedron. Icosahedron. Okay. So what about 5 and 4? If I plug in 5 and 4 here, is the same as this impossible situation. So whether you have 5 or 4 here, it doesn't really matter. 5 and 4 would be another impossible combo. That is also impossible. And 5 and 5, also impossible. Impossible. Since 2 over 5 plus 2 over 5 is equal to 4 over 5, and that is not greater than 1. So out of all possibilities, what do I have? I have only 5 that we already know. 1, 2, 3, 4, 5. These are the ones that we already know. So no matter how hard we try to find another possibility, there isn't another possibility. It's only the 5 that we already know. So this means that there is only 5 possible combinations, and these are the ones that we know, the ones that we know. And that would be the end of the proof. It's really nice, actually. I repeat, this is not the proof that Euclid gave in Elements, but I thought this was very nice as well, so I thought of introducing you to this proof. It's fairly simple. Okay, before I conclude part 2, I want to bring something up here, see if you can notice any pattern in this table. Look at the following. Look at the cube and octahedron. Cube and octahedron, the number of faces of octahedron is the same as the number of vertices of the cube. And the number of faces of the cube is the same as the number of vertices of octahedron. Yet the number of their edges is the same. Same thing for dodecahedron. The number of vertices of one is equal to the number of faces of the other, and they share exactly the same number of edges. This is not actually accidental. It has to do with something called duality. It's a property that regular solids enjoy. I'm not going to define what duality is, because duality is a concept that to be defined would be a bit beyond the scope of this class. But I just want to explain a little bit. These two solids are called duals of one another. What does that mean visually? Visually, that means that you can embed one inside the other in such a way that the corners of one are looking at the vertices of the other, and vice versa. So the corners of octahedron are looking at the faces of the corners of the cube. If you put the cube inside the octahedron, the corners of the cube are facing the faces of octahedron, and vice versa. There is some sort of embedding between the two, and they have the same number of edges. So it's very difficult to actually draw it, but here is a picture. I have embedded the cube inside the octahedron. So the red is the cube, and if you can make it out, I don't know if you can, but this was probably the best picture, transparent picture I could find in the net. So look at the cube is inside the octahedron. For example, this face of the cube is looking at this corner of the octahedron. This face of the cube, this other face of the cube, is facing this corner of the octahedron, and so on. So this face is looking at this corner, and this other face is looking at this corner, and so on. And they have the same number of edges. So that's why we say that octahedron and cube are duals of one another. Here's another picture for dodecahedron and icosahedron. They are also duals of one another, although it's a little bit more difficult to actually see. It looks like a lot of lines, but hopefully you can see something. The green ones are the vertices of the dodecahedron. So, for example, look at this face. This face is of the icosahedron, is looking at this corner of dodecahedron. Or for this other face of icosahedron is looking at this corner of dodecahedron, and so on. So these two are also duals of one another. And I don't have a picture for tetrahedron, but tetrahedron is a self-dual. It can be embedded in itself. This was just to point out this nice property of duality, but I have no intentions of talking about the duality of regular solids in this course. I just thought it was something nice to point out, among other things. Okay, that would conclude lecture 5, part 2 of lecture 5, and you will hear from me next time. So long.